Welcome to This Explainer. Today, we're unpacking something genuinely mind-bending, the incredibly ambitious project known as ARGUS. Now, I want you to just picture the sheer scale and complexity of operating a modern particle accelerator facility. We're talking about one of the most advanced scientific instruments on the planet, literally pushing the boundaries of human knowledge in nuclear physics. Operating a machine like this isn't just your standard technical challenge, it's a monumental feat of coordination. So ask yourself, how exactly do you run a machine with thousands of moving parts? And I'm not just talking about physical gears and wires here. We're talking about thousands of live operational signals that have to be continuously monitored in real time. Every single sensor, vacuum pump, and magnet has to work in perfect harmony. And when something goes wrong, the operators in the control room need to figure out exactly why. And they need to do it fast. Okay, let's dive into this, because the reality of how these highly advanced facilities are managed right now might actually surprise you. It's totally fragmented. The information needed to run these machines is scattered everywhere. It's buried in dense technical PDFs, clunky electronic logbooks, maintenance inventories, and honestly, a huge chunk of it is just stored as tacit experience in the minds of a few senior experts. It's like a giant puzzle where half the pieces are in different rooms. Compare that to the ultimate dream: a single, unified, centralized AI operating system. Here is our roadmap for today. We're going to cover the accelerator knowledge crisis, introduce the ARGUS AI brain, break down how the architecture works, look at the absolute need for security, walk through the real-world rollout, and finally, explore the future of trustworthy AI. Section 1, the accelerator knowledge crisis. This right here is the main bottleneck for scientific facilities today. The core of this crisis is the massive disconnect between live operational data and structured knowledge. Picture this: an alarm blares in the control room. The operators see the live data flashing red on their screens, but to figure out what it actually means, they might have to hunt through disconnected technical manuals, query some legacy database, check maintenance logs, or just cross their fingers and hope the one expert who knows how to fix it happens to be on shift that day. Relying on these disconnected systems creates a huge bottleneck during crucial troubleshooting moments. Moving right along to Section 2, enter ARGUS, the AI brain. ARGUS is an AI-native knowledge operating system proposed by INFN, Italy's National Institute for Nuclear Physics, and it's planned for a 36-month rollout. I absolutely love this quote straight from their proposal. The concept is so bold: give a large language model access to all the knowledge that exists about a facility. They aren't just building a glorified chatbot here, they're building a master brain with a unified memory that pulls together procedures, asset inventories, troubleshooting histories, and real-time operational data into one place. But let's be real, you can't just plug standard ChatGPT into a particle accelerator, right? AI makes things up, it hallucinates. To defeat that, ARGUS uses a hybrid retrieval-grounded system. Let's demystify that jargon. Basically, it means the system combines smart document search with a highly structured knowledge graph. The AI is literally tethered to the facility's actual data. If it doesn't have the verified INFN source document or live data point, it stays quiet. Every single AI answer is explicitly linked to the source documents, ensuring full audited traceability. So the crucial point is this 50% target. The ARGUS project specifically aims for a 50% reduction in unsupported or fabricated answers compared to a standard ungrounded baseline AI model. Because in a mission-critical control room, accuracy isn't just a nice-to-have, right? It's an absolute necessity. Section 3, how the architecture works. Let's pop the hood and see how this master brain reads, remembers, and reasons. And this brilliantly illustrates the whole closed loop. It starts with pulling in raw data from the control systems and standard procedures. That flows right into the knowledge graph and vector database. Then it hits the language model for reasoning. But notice the safety guardrail and audit layer at the end. The AI can't just decide to poke the accelerator. Every single action has to pass through strict, audited human-in-the-loop interfaces. The whole thing runs on strictly decoupled microservices. Here are the 5 steps. First, data acquisition from the facility. Second, ingestion and chunking of all those complex documents. Third, retrieving the cold hard facts using the knowledge graph. Fourth, running the language model inference based strictly on those facts. And fifth, executing those audited human-in-the-loop actions. By completely separating the control plane from the AI plane, they guarantee ultimate safety. The AI advises, it doesn't blindly act. Section 4, the need for security. This is a massive challenge regarding data sovereignty. You see, IFNN can't exactly beam top-secret particle accelerator data and sensitive administrative info up to a public cloud AI service. That would completely violate their strict data governance policies. So ARGUS requires a highly secure, on-premise hardware solution. They use what are called confidential containers to strictly isolate all that sensitive operational data natively on their own servers. To pull this off, the architecture is split into two distinct tiers. You've got the operational brain, a dedicated on-premise AMA 805 server packed with 4 H200 GPUs. That handles the secure, always-on production services for the operators in the room. Then, separate from that, you have the research brain, running on federated high-performance computing resources on the IFNN data cloud. That side is for offline research, fine-tuning, and testing out new open-source models. Section 5. Real-world AI operations. Let's see how this ambitious plan actually gets deployed. Let's move to and see how this builds across the 36-month timeline. By month 9, the secure on-premise AI infrastructure gets installed. Month 15, the first unified knowledge layer gets populated with real data. By month 27, we get a functional prototype of the operator dashboard with grounded chat. And finally, by month 36, the whole system undergoes final validation testing on live beamlines. What I find super fascinating here is the dual nature of the whole project. On one hand, ARGUS delivers immediate, trustworthy operational tools, stuff like a Q&A dashboard for documentation and intelligent incident management to help operators troubleshoot on the fly. But simultaneously, it's pushing the envelope in research, figuring out how to expose complex machine learning tuning and parameter optimization tools so that the AI can call upon them naturally down the road. But again, let's reassure everyone, this master brain isn't Skynet autonomously taking over the facility. The system operates primarily in a read-mostly mode. The operator UI includes explicit citations for every single recommendation it makes. If the AI suggests tweaking the machine, those agentic actions are strictly rate-limited and absolutely require human-in-the-loop confirmation. It is a highly intelligent, supervised advisor, not a rogue pilot. Finally, Section 6, the future of trustworthy AI. What does all this mean outside the realm of nuclear physics? By building a system that is secure, grounded, hybrid, and reproducible, INFN isn't just solving their own local problem. They're basically creating a gold standard reference architecture for sovereign, explainable AI that aligns perfectly with the EU AI Act. They're proving, right now, that you can deploy highly capable AI in extremely sensitive environments without sacrificing an ounce of safety or data privacy. And honestly, that blueprint is desperately needed everywhere. High-reliability industrial sectors face the exact same fragmented knowledge headaches. Think about advanced manufacturing plants, massive distributed sensor networks, energy sector operations, and complex transportation infrastructures. They all rely on thousands of moving parts, scattered manuals, and tacit expert knowledge. They could all adopt this exact same master brain blueprint. Which leaves us with a truly fascinating thought. We are actively watching the dawn of highly secure, strictly grounded AI agents working safely in one of the most complex scientific environments ever built by humanity. So I'll leave you with this question to ponder. If an AI can be trusted to help master a particle accelerator, what mission-critical facility is next? Thanks for joining me on this explainer, and keep learning.